all of the either.
If they stayed apart, then some electrons would have transferred, but they went back, so therefore nothing transferred. All right, so we talked about an insulator. Insulator, the electrons are not going to move particularly freely. We assume an ideal insulator, the electrons are basically going to stay with it, whatever atoms assigned to them. This is metal. Always assume metal is a conductor, unless otherwise stated. We have an insulated material right here. This little black disc here is insulation. This is a metal box here, but this black disc, which I assume is bakelite, is keeping the metal from touching this metal. And so I have metal, the metal knob here, the pole, and then these two leaves here are metal also. So as I bring it closer, I got electrons on here. What is it going to do to this?
Well, other than the leaf separating?
Yeah, I mean, we're trying to get to why the leaves separated. What do I know electrons will do?
The electrons will stay there, but if somehow it were to get through to the conductor, it would go down into the metal leaves.
So you're going with the transfer idea?
Yeah. Well, no, not. But it's not transferring. So.
If it let's just see what it looks like if it transfers.
Is it something to do with like electrons flow kind of like water, and that's the easiest path for it to go down?
Which electrons?
Your excess static electrons that you're like putting into your insulator.
Now, all right, so let's take a look. If I touch it, they go way far apart. I take it away, they're still far apart. That's how I know something got transferred, because this comes away and they're still far apart.
That makes sense.
All right. Another key word, grounded. I grounded it just in. A ground is basically either a place where you dump excess electrons or pull excess electrons. So when I touch it, electrons transferred. I now have an abundance of electrons there. They hate each other. Don't forget, like repels. The electrons hate each other. Even though they can't tell each other apart, they still hate each other. And so they spread out as far as possible. However, without touching it, the leaves still spread apart. There was a statement earlier that what would cause these to spread apart is if they had the same charge, which is appropriate for this, of course. But why would they have the same charge when I brought this near it but didn't touch?
There was a transfer of electrons.
Pardon?
There was a transfer of electrons.
No, transfer from what to what?
From the pipe to the metal.
No
Repeat
transfer.
the question.
Why is it that when I brought this near, the leaves move farther apart? Recharge this since I got rid of some. Why do the leaves move farther apart when I bring it near it, but don't actually touch it?
Is there some sort of like feel, like when you can feel the static on clothes when on the dryer?
Okay.
When you're not close to them. So I don't know. There's some type of disturbance.
It's false.
The aluminum wing charge is opposite from like the tube charge.
Oh, you're saying that the leaves are positively charged?
Yeah, so they have like opposite charges, so that's why like when you're, or no, they have like the same charges, so that's like why when you're getting close, they repel.
Well,
Then whenever you like pull it away, they come back.
why do they have the same charge though? Because right now it's neutral. I have just as many electrons and protons in that thing. It was actually mentioned before when I talked about charges, but it also shows up here. If this has electrons in it, and I bring it close to something, If any of you ever rubbed a balloon against your head and
Yeah.
stuck it to a wall,
A what?
a balloon.
Oh, they said a bullet, I was like,
If you can do it with a bullet, more power to you, but. A balloon. Rub against your head, stick it to the wall. What's it sticking? What causes it to stick?
Static electricity.
Okay. Perhaps that wasn't the way to go then. All right, so valence electrons were mentioned earlier. What are valence electrons?
Extra electrons that aren't supposed to be there necessarily.
The electrons on the shell that are rotating around the nucleus.
Yeah, it's the ones most likely to be transferred. They're the ones that move most easily, because they're the farthest from the nucleus. So as I bring a negatively charged object towards this, what happens to the electrons here?
They're pushed away from the field ones from the pipe
And where do they go?
down into the rod.
And ultimately,
So it doesn't transfer, it repels from above.
right,
Okay.
it chases the electrons here away, so these electrons, not all the electrons, but enough of the electrons here get chased away and they go into the leaves, making the leaves negatively charged, they separate. When they pull this away, they go, all right, we can go home now, and they return. No one gave the wrong proton answer, which I appreciate. So, another really good rule of thumb to keep in mind. That's supposed to be a Y there. In everyday life, it's the electrons we can move. Should actually be that. Yeah, the protons in there are attractive, but the protons aren't going to move. Well, actually, not in the way that you talk about the electrons moving. If I want to move the protons in this table, what would I have to do to move the protons in the table?
Nuclear fission?
Something simple, something I could do right here in front of you.
Cut it in half.
Something less dramatic. Cut it in half. Well, that probably might work.
we're back.
All right, I'm about to move the electrons in this table. Here we go. Thank you very much.
It's a Nobel.
That's right. The protons are bound to the nucleus. The way that you move a proton, for the most part, unless you're going to really go into something dramatic like fission or fusion, is you're moving the object itself. The protons are not going to flow up to the top when I bring a negative charge towards it. It's the electrons that get chased away.
That makes sense.
So, all that's well and good. Oh, first off, when I run the rabbit fur against the BBC, I made the claim that it's electrons being transferred to the pipe. How do I know that electrons are being transferred to the pipe as opposed to the rabbit fur?
Other than you feel it?
All I would feel, I mean, if this were positively charged, I would still feel that too.
You made the claim earlier that PVC was an insulator.
Yep.
Does it have more insulation properties than rabbit fur would, thus making it a better candidate to change over?
Not for that reason.
Okay.
Because there are other insulators which would pick up positive charge. Although as a general rule of thumb, plastics will pick up electrons, but how would I know that? Why would I make that such a claim?
Have you ever been shocked through plastic?
through plastic.
Yeah.
That's a good.
How would you know?
Yeah.
Like, how would you know that it's like an insular or whatever?
No, how would I know that the electrons got transferred from the rapid furrow to the pipe as opposed to the other way?
Oh. I'm pretty sure they taught me this in chemistry, but
Alright,
something like one of them has to lose them.
okay,
And you can know that because of whatever atoms are. You know for a fact, some of them want to receive electrons and some of them want to give away electrons.
okay. So how do I know this wants to receive and that one wants to give away?
How do we
Because of the
know?
material?
The amount of valence electrons on the outer
Let's do it.
ring.
What we're,
I've never seen it connected to the number of valence electrons on the outer ring.
so what we're trying to diverge to is you're saying one of them is a cation, one of them's like an anion? Or is this just the wrong rabbit hole?
Wrong rabbit hole.
Wrong guy.
Alright. Alright,
The
so,
rapid losses.
Like 0 and 10
I cannot erase it with my finger. Triboelectric effect. Now, we have charge sensors, and I could do that experiment and then put this into a receptacle connected to the charge sensor, and we could actually see that it's negatively charged. But somebody's already done that for us. It's not a particularly sophisticated answer, but somebody's gone through and done a whole lot of comparisons of materials just to see which one is more apt to gain and which one's more apt to lose.
Okay.
So if you do a search on triboelectric effects on the internet, then you often will just get a list of materials, and the ones typically higher up in the list are more apt to get positively charged. The ones on the lower in the list are more apt to get negatively charged. So it's found experimentally.
So it's based on experiments, the material is the cause of what transfers?
Yeah.
Okay. Yeah.
Oh, okay.
But is there like a sort of like rule or like consistency, or you just have to like manually test everything?
I have not been privy to anything more sophisticated than somebody's gone through and they've done the testing.
Okay.
I'm getting, like, because it just makes sense that they do all the testing and then they find trends within the results, right?
Yeah, I think part of the problem is that, like with friction, engineers have a system that works, and physicists are worried about other things. So there is a group at NC State that is studying, trying to come up with something more sophisticated. Well, at least with friction, but they do tribology, which is basically from the Greek word for rubbing.
Oh, that makes sense.
But the formula for friction has been around for a couple hundred years, and no one's really come up with anything better, and they're trying to. They might have done it by now, but the talk I saw was a couple years ago.
So you're telling me if they figured this out, that'd be like a big accomplishment? That'd be the first time they've changed it in like hundreds of years?
Yeah, but I suspect the textbooks aren't gonna change, because again, most of you are future engineers, of some form or another, and we got something that works.
Yeah.
So, do you need something more sophisticated?
No.
Probably not, but depends on what you end up doing. All right, let's crank it up even more.
Oh.
Probably not on the metal.
Got rubber wheels on it.
The knob is concerning.
Yeah, it's all the way up. It's
And it looks like it's on too.
Yeah, I think, yeah, your dead switch.
It probably is on.
That was about to get great, man.
Just turns it on, it's like, well, class is over.
Everyone died.
Speaking of dying, I now have this. We're doing this experiment. My first year, I had not found this yet. So I'm in a 110 class in the Volta Van de Graaff generator, and I'm really nervous about the electricity at this point. I've been shocked way too many times.
That can't be fun.
Can't tell if
I
it's
was
bad.
doing some work on one of the outlets in one of our houses, in an older house, and
Sorry.
I turned to my wife, "Did you turn the power off?" "Yes, I did." Apparently not to the outlet I was working on.
Dr. Fox, I could sympathize.
All right, now the reason I'm doing this is that I want to be able to turn it on and off with my foot. And sometimes this gets charged, which is the reason I pulled it off of this, and sometimes that will get charged as well. All right, what's gonna happen here is when you turn it on, the belt's gonna slip and get some material down here. And I used to have the screws out of it and then lost the screws, but it was convenient because then I could show it to you more easily. But it's gonna slip on the belt, and the belt basically is gonna become positively charged. As the belt comes up here into the top, it's gonna pull electrons from here. The electrons will go onto the belt, come down here, and the electrons get bled off. So the belt remains positively charged, and you just keep sucking more and more electrons from here. Let's start with this off. Oh yeah, so that first year, sorry, I was doing he didn't die. I was really nervous about turning it up. I had it like 50%. And one of the students goes, "Dr. Fox, crank it up!" No. No, come on, crank it up. No. All right, I'll hold the wand. And it was a wand about this big. And so I said, okay. So he was holding it like this. The electrons shot from his fingers that were just on the outside of it, from his fingers to the ball when it was about this far away. Yeah, that was not good. It hurt.
So we're never turning it up.
You never what?
We never turn it up.
Oh, well, we can now because I can stand farther away.
Oh, okay.
There we go. Right down. I've also been dealing with electricity more than I used to, and I also have a rubber glove now.
Ah.
All right. We've got electrons being transferred there. See if we can actually see it. There we go. All right. So in theory, this is positively charged because electrons get sucked from it. When you see the spark, that's electrons being transferred through the air. Now, in June or July, if you're doing this as a summer course, this thing would have been drained already by then. Yay. Living in the south, there's humidity. But potentially it's still charged well enough, and so you should be able to hear it when I now touch it to the board. You heard that?
Yeah.
I heard it.
I heard it like pop.
All right. So apparently I waited too long.
On that
Part
first
that I hate.
smack, there was that, you could hear it, you could hear that.
Yeah, the first time.
I
You
could
hear
hear
it
it.
go
Yeah, that first smack is because I'm.
No, there was a secondary, you could hear
Yeah.
the electricity.
You can hear it.
And just so you know that I shocked myself when I touched this.
Thank you for your service.
Hey, sir. Sacrifice is worth it for you guys.
I'm not sure about that.
All right, so this is an insulator. It's a
Packing cool?
packing unit, yes. I'm gonna turn this on. The question is what's gonna happen when I bring it near it. hopefully, it's not going to pull electrons from my hand through the glove. See if we can actually, don't know if this is gonna work, but let's try it.
Oh no. Chuck it. Ah. Ah. It's repelling. You didn't shock yourself again.
I have not. Now notice when I flicked it towards it, it got repelled.
Yeah.
I was touching it before I put it on there. I mean, it's neutral. Why was it affected by the charge there if it's neutral?
So maybe when you were touching it, like holding with your hand, the same thing with the PVC and the rabbit fur, like your skin is, and the packing peanut, since it's an insulator, it's or more of an insulator, it's more
So-
likely to.
So you say the electrons went from my hand to the peanut? Through the
No,
rubber?
no, the electrons, because that you said that's positively charged.
Yes.
So the electrons from the peanut went into your body, and then
Through the glove.
oh, you're holding with the glove.
Yeah, I had it with the glove down. Well, I neutralized it with this hand, then I put it on the glove.
Are we explaining why it repelled back?
Yeah,
Is it just because of the fact that it's neutrally charged, it doesn't have a positive or negative, you have all these positives pushing out, it just doesn't have any effect really with it?
I couldn't hear any pop of anything being transferred between the two, so
No.
this, I think we can generally assume that this stayed neutral.
But it did it like a magnet. It would, I don't know.
You missed it earlier, let's stay away from magnets till we get to chapter
Oh,
30.
oh, okay. No magnets on, okay.
Is it just that it's not exactly neutral?